Hi everyone. Here you are going to learn about a very important topic, and you're going to learn on how to create the generator polynomial and the parity check polynomial. Okay, you see, because in the last video you learned some of the important properties of the generator polynomial. Okay, so we are going to apply those properties in this video. One of the property, we know that the degree of the generator polynomial is n minus k. Okay, now what is the other property is that the first coefficient and the last coefficient of the generator polynomial must be equal to 1. That is the coefficient of the first term as well as the coefficient of the last term should be equal to 1, because unless and until these two coefficients are equal to 1, that is the coefficient of the first term and the last term must be equal to 1. Unless and until they are equal to 1 only, we will get a degree of n minus k. That is the degree of the generator polynomial must be exactly equal to n minus k. It should not be less than n minus k or not greater than n minus k, but exactly equal to n minus k. So to ensure that the first coefficient and the last coefficient of the generator polynomial must be equal to 1. So these are the two properties, and one more property that we have also learned is that we know that the output polynomial, the code polynomial v of x, is a factor of x raised to n plus 1. So if that polynomial is a factor of x raised to n plus 1, then g of x is also a factor of x raised to n plus 1. Or in other words, another property we have learned is that g of x is a factor of 1 plus x raised to n. This is another property. So these are the three essential properties of any generator polynomial of a nk cyclic code. Let it be systematic or let it be non-systematic. Any cyclic code, nk cyclic code, the generator polynomial must satisfy these three properties. That is, it should be exactly equal to n minus k, the degree must be exactly equal to n minus k, and the first coefficient and the last coefficient of the generator polynomial must be equal to 1, and also it should be a factor of 1 plus x raised to n. Okay, so in that case, now I'm going to tell you how to create. First, I'm going to tell you how to create the generator polynomial. So how to create the generator polynomial is that, let's take an example. So with that example, we can tell you how to create it. See, let me take an example of an nk cyclic code. I'm going to make it a 7-4 cyclic code. Okay, a 7-4 cyclic code. So I'm going to create the generator polynomial of a 7-4 cyclic code. Okay, it's a very easy step. So 7-4 cyclic code, what are the basic properties of the generator matrix? That is, the g of x must have the degree must have a degree of equal to 3, right? And also the first coefficient and the last coefficient. So we all know is if the degree is 3, then we can express the generator polynomial in the form of g0 plus g1x plus g2x square plus g3x cube, right? So this is my g of x. Yes, because the degree should be exactly equal to 3, which means they should have this, the degree, this x cube must be there, this x cube should be there. So this is the degree, this is a polynomial of degree 3. And remember that all these values that you see here, g0, g1, g2, g3, they are all nothing but binary values, which means they can either be 0 or 1. Okay, but now let's look at the second property, that is, the first coefficient and the last coefficient must be equal to 1. That is, the value of g0 and the value of g3 must be equal to 1. So therefore, from the second property, we have learned that g of x is equal to, or can be expressed as, 1 plus g1x plus g2x square plus x cube. You see, here you can see here that g0 is equal to 1 and gn minus k. N minus k means 7 minus 4, which is g3. So g3 is also equal to 1. So therefore g0 and g3 is equal to 1. So you get this polynomial. So this is the polynomial of the generator. This is the polynomial of the generator g of x. So now the thing is, you need to find the value of g1 and g2. Now you need to find the value. All you need to do is now find the value of g1 and g2. So that is the problem now. So how to find the value of g1 and g2? You know the g1 and g2 can either be 1 or 0. Either one of them will be 1, the other will be 0, or both of them will be 1, or both of them will be 0. It can be any of these values, but the thing is, we don't know. So how to find the value of g1 and g2 is, you simply look at the third fact. That is where the third property comes into the picture. That is, g of x must be a factor of 1 plus x raised to n. Here the value of n is 7, which means g of x is a factor of 1 plus x raised to 7. What is the meaning of the term? What is the meaning of factor? Factor of x raised to 7 means if you divide this by g of x, you won't get any remainder. You are not supposed to get any remainder, or the remainder is 0. That is the meaning of factor. So therefore, g of x is a factor. So if this polynomial should be a factor of this, then the remainder should be equal to 0. So now what I'm going to do is, to get the remainder equal to 0, I'm going to divide this by this. Okay, that is, we know that here for nk, here n is equal to 7. So I'm going to divide 1 plus x raised to 7, or x raised to 7 plus 1. I'm going to divide x raised to 7 plus 1 with this polynomial, and then I'm going to find its remainder. So x cube plus g 2x square plus g1x plus 1 divided by x raised to 7 plus 1. Okay, always when we are doing a division, always we start by writing the higher order coefficients first, the higher order terms. Okay, so in that case the division process will become simple. You can either start with 1 plus, and here also 1 plus. You can start with the lower division, but the calculation will become more difficult at the end. So start with the higher order coefficients. For any operations, it's always better that you start the operations from the higher order first. Okay, so here in this operation, what I'm going to divide this. Okay, since I know that, so the problem here is that I need to find the value of g2 and g1. Okay, so in order to find the value of g2 and g1, what I'm going to do is, I know that according to the third property, this g of x is a factor of 1 plus x raised to 7, or x raised to 7 plus 1. I know it's a factor of this. So what I'm going to do is, I'm going to divide this, and then I'm going to find its remainder. And then what I'm going to do is, I'm going to equate that remainder to 0. In that case, then by equating the remainder to 0, I can find the value of g2 and g1. So that is what I'm going to do here. So I'm going to divide this. So on dividing this, how to divide is that the first term should always get cancelled each other. Remember, this division is not like your normal division. As you said, this division is actually more simpler than your division. It is actually more simpler than the actual mathematical division, because the plus operation, the addition operation, and the subtraction operation are nothing but your XOR operation itself. There's nothing new here. Everything is XOR operation, whether it is a subtraction or a addition. And also the multiplication is nothing but the AND operation. Okay, XOR operation, I'm going to tell you again, XOR operation means 0 XOR 0. Instead of saying 0 XOR 0, I will say 0 plus 0, because XOR is also equivalent to sum operation also. So let me say 0 plus 0. So 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 0. That's all. That is the XOR operation. Now, the multiplication is equal to the AND operation, which is 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. So that is what we are going to do right here. Everything is nothing but AND operation and XOR operation. So I'm going to divide this. First I need to cancel the first. Every step I need to cancel the first term. So in order to cancel this term, I'm going to multiply this with x raised to 4. Then only this term will get cancelled. So I will get over here x raised to 7 plus g2 x raised to 6 plus g1 x raised to 5 plus x raised to 4. This is the first step. Okay, so what will happen is that these two will cancel each other. Okay, so what will I get? I will get the remainder g2 x raised to 6 plus g1 x raised to 5 plus x raised to 4 plus 1. This is what I got. Okay, so now what I'm going to do is that I need to multiply one term with this so that I will get g2 x raised to 6, so that those two will be cancelling each other. So in that case I will multiply this with g2 x raised to 3, right? Because if I multiply x raised to 3 with g2 x raised to 3, I will get g2 x raised to 6. So on multiplying them, I will get the first term will be cancelling each other, g2 x raised to 6, because they both are same, plus the remaining set g2 x cube into g2 x square. So like I said, it's an AND operation. So what is g2 dot g2? g2 dot g2 is g2 itself, because 0 into 0 is 0 and 1 into 1 is 1. Both are the same value. So therefore g2 into g2 is g2. So it is g2. Okay, don't ever think of making a mistake saying that it's g2 square. There is no square here. These are all binary values, right? So it can either be 1 or 0, nothing else. So we think of it like that. So this is g2 into g2 is g2 itself, and x cube into x square is x raised to 5. Okay, next is we multiply this with this term. So you will get g1 g2 x raised to 4, plus we multiply this with this term and you will get g2 x cube. See, so this is what we get. So now what I'm going to do is I'm going to XOR everything what I'm seeing here. In that case, these two will get cancel each other, and here these two are the coefficients of x raised to 5. So which means the coefficients of x raised to 5 is g1 plus g2. g1 plus g2 is the coefficients of x raised to 5. Okay, when I say plus, again I'm telling you, when I'm saying plus I meant XOR operation. Okay, so always think like that. Now next will be this thing. So plus, so this is 1 plus g1 g2 x raised to 4 plus g2 x cube plus 1. So this is the next step. So now what I'm going to do is that I'm going to multiply this with, now I want to cancel this term from here, right? I want to cancel this term. So what should I multiply that with here? I will get I will multiply it with g1 plus g2 x square, right? If I multiply g1 plus g2 with x square with x cube, I will get this first term. So those two will cancel each other out. Okay, now I'm going to write the remaining term, but this if I multiply this with this. So just see for yourself what will happen if I multiply this with this. Okay, of course you will get x raised to 4. I admit that you will get x raised to 4, but what else? What else will you get? You see, what will happen if I multiply g2 inside the bracket? If I multiply g2 inside this bracket, I will get g1 g2 plus g2 g2, and g2 g2 is nothing but g2 itself, right? So I will get g1 g2 plus g2. So therefore g1 g2 plus g2 x raised to 4 plus, then if I multiply this with this, I will get g1 g1 plus g1 g2, but g1 g1 is g1 itself, so I will get g1 plus g1 g2. So this is nothing but g1 plus g1 g2 x cube plus, and this is g1 plus g2 x square. See, this is how we get. Now what I'm going to do is that again the first term will be cancelling each other, so I will cancel them and you write the remaining terms. So that's the interesting part. See over here, look over here, if I'm going to XOR all of them, you can see for yourself that both of them have the same coefficients, which means they will cancel each other out, because 0 plus 0 is 0 and 1 plus 1 is also 0. So g1 plus g2 plus g1 plus g2 is actually 0, right? g1 plus g2 plus g1 plus g2 is also 0. So therefore the remaining value will be 1 plus g2 only. So it will be 1 plus g2 x raised to 4 plus, now what about x raised to cube? X raised to cube, there's nothing new over here. I need to add all of them together, right? So you will get, how to write it? I will write like this, that is g1 plus g1 g2 plus g2 x cube. Okay, These are the two coefficients added together, so you will get the entire coefficients. Nothing will be removed. Next you have is g1 plus g2. There's nothing over here to cancel them, so it will be g1 plus g2 x square itself. Let me write that, g1 plus g2 x square, that's it, plus 1. Okay, so now what I'm going to do is I'm going to find a value to multiply, so that if I multiply it with this, the first term will be cancelled. So I will multiply it with 1 plus g2 into x. Okay, so because if I multiply 1 plus g2 into x with x cube, I can cancel the first term. So it will be 1 plus g2 into x raised to 4 plus, and what about the remaining terms? The remaining terms I will get is, that's the beauty of here. Look over here. What are the remaining terms is, here you see g2 into this value, into this bracket. So what do you get? You will get g2 into this is nothing but g2 plus g2 into g2, right? g2 plus g2 into g2. g2 into g2 is g2 itself. So you get just nothing but g2 plus g2, and g2 plus g2 is nothing but 0. So therefore, if you multiply this value with this value, you will actually get 0. So you don't have to write it down. You will get 0. Let me write that. You will get 0 actually. Okay, this value multiplied with this value, you get 0. Okay, because XOR functions are basically nothing but AND operation and XOR operation. Okay, so you will get over here g2 plus g2 into g2, but g2 into g2 is g2 itself. It's an AND operation, so g2 into g2 is g2 itself. So g2 plus g2 is 0. That's why it became 0. Now that's about this. And what about the other term? The other term will be, you will get g1 plus g1 g2, right? So you will get over here g1 plus g1 g2 x square. Okay, that's it. Plus you will get then what else will you get? Then you will get 1 plus g2 x. You will get 1 plus g2 x plus, that's it. Yeah, that's it, right? That's it. I have not missed anything. 1 2 3 4 1 2 3 4. Okay, so now I can do is that I can do the XOR operation again. So the first terms will cancel each other, and the remaining terms will contain the value g1 plus g1 g2 plus g2 x cube plus, and what about this? If I'm going to add these two, you see g1 and g1 is there, so g1 plus g1 is 0. We know that g1 plus g1 is 0, so you're left with g2 and g2 plus g1 g2. So you will get g2 plus g1 g2 x square. Okay, x square plus, and what about x? X is alone, right? X doesn't have any companions, so you will have 1 plus g2x plus 1, right? So this is the values you get. Okay, so now what I'm going to do is I'm going to multiply in one value with this, so that I will one value with this, so that I will get this. So what should I multiply? I can multiply this here. The coefficient x cube, here is also x cube, so just simply put a constant, and the constant will be g1 plus g1 g2 plus g2, g1 plus g1 g2 plus g2. This is the value. So this multiplied with this, I will get this, so I can cancel them. So I will get g1 plus g1 g2 plus g2 x cube plus, now if I multiply this with this, I will get, what will I get? Let me see. I will get g2 into this is nothing but, just mentally calculated, g2 into this. You will get g1 g2 plus g1 g2 plus g2. Again, I repeat it. If you multiply this with this, you will get g1 g2 plus g1 g2 plus g2. So actually it is g1 g2 plus g1 g2 plus g2 into g2, but g2 and g2 is g2 itself, and also g1 g2 plus g1 g2 is 0, so which means you will be left with nothing but g2 x square. Okay, plus, and if I multiply this with this, again the story is same. You will get G1 into G1 plus G1 G2 plus G1 G2. But G1 G2 plus G1 G2 is 0. So you will get G1 itself. So you will get G1x. G1x plus, and if you multiply this with this, you will get 1 with this, you will get G1 plus G1 G2 plus G2. And now what I'm going to do is I'm going to XOR everything, and here the first term will get cancelled and the remaining terms will be, here you can see that the G2 and the G2 are same over here, so therefore if I XOR them, they will get 0, they will cancel each other, so you will get G1 G2 x square plus, and if I XOR these two values, I will get 1 plus G1 plus G2, sorry, 1 plus G1 plus G2 x plus, and the last term will be G1 plus G2 plus G1 G2 plus 1. There. This is the remainder. This is my remainder. Let me write my remainder clearly in the next page. Okay, so the remainder I got was, let me write it again. So now you can't further divide this because the coefficient over here, the degree over here is less than 3. Right? So you can't multiply anything here so to get less than this. So this is the least value you can, if you go through. So this is the remainder. So the remainder is, let me write it again, G1 G2 x square plus 1 plus bracket 1 plus G1 plus G2 x plus, and the remaining will be what are the remaining will be G1 plus G2 plus G1 G2 plus 1, sorry, I forgot that, plus 1. This is the remainder polynomial. Okay, so what I just did is that I divided x raised to 7 with my generator polynomial so that I got this remainder. But I have already told you that one of the essential properties of the generator polynomial is that it should be a factor of 1 plus x raised to 7. Here n is equal to 7. So here it's a factor of it, right? So factor means the remainder should be 0. Remainder 0 means this polynomial should be equal to 0, and this polynomial can only be 0 only if each of its coefficients are equal to 0. Alright, so if you want this remainder to be 0, then each of the coefficients inside this polynomial must be equal to 0. What I meant is that G1 G2 should be equal to 0, 1 plus G1 plus G2 should be equal to 0, and also G1 plus G2 plus G1 G2 plus 1 should also be equal to 0. Because unless and until these coefficients become 0, then only the remainder will become 0. So it will become 0 into x square plus 0 into x plus 0. You see, because this is actually the coefficient of x square. G1 G2 is the coefficient of x square. This is the coefficient of x. 1 plus G1 plus G2 is the coefficient of x. And this is the coefficient of x raised to 0. That is G1 plus G2 plus G1 G2 plus 1 is actually a coefficient of x raised to 0. So each of these coefficients must be equal to 0. Then only the remainder will become 0. So your job is to find the value of G1 and to find the value of G2 so that all these three equations will be satisfied. All these three equations means the first equation is what? G1 G2 is equal to 0. Okay, G1 G2 is equal to 0 is the first equation. What is the second equation? This is the second equation. Second equation is actually G1 plus G2 is equal to 1. This is actually a second equation. Okay, same, both equations are same. 1 plus G1 plus G2 is equal to 0 is also same as saying G1 plus G2 is equal to 0. Remember, there is no minus or subtraction or anything like that in this function, in this binary values. And this plus or the sum operation we are saying here is actually the Xor operation. Okay, that is why. So everything is so simple. There is no minus or anything. So if 1 XOR G1 XOR G2 is equal to 0, then definitely G1 XOR G2 is equal to 1. That's what it means. In the same way, over here also, G1 plus G2 plus G1 G2 plus, is equal to 1. Okay, and here, like I said, what this equation actually means is that G1 XOR G2 XOR G1 G2 is equal to 1. That is what this means. That's all. Okay, so what you're going to do is you need to find the value of G1 and G2 so that all these equations will be satisfied. So what are those values? You see, you can use any kind of common sense, any kind of logic reasoning you like, in any way you want. For example, here you can say that this is an AND operation. So G1 G2 is equal to 0 means we know that this is 0 only if one of them is 0 and the other one is, yes, only if one of them is 0 or both of them are 0. But if you look at the third equation, here G1 plus G2 is equal to 1. So what does this mean? This actually means is that one of them is 0 and the other one is 1. Because other than that, only on that occasion only, this will become 1, right? Either it should be 0 XOR 1 or it should be 1 XOR 0. Then only this equation will be satisfied. So also this, which means the only way of satisfying all these three equations is either if we choose G1 is equal to 0 and G2 is equal to 1, or we choose G2 is equal to 0 and G1 is equal to 1. So we can either choose. The reason is both of them are correct. You can either choose this or you can either choose this. Choosing any one of them is okay for you. But once if you choose one, don't change it. You are not supposed to change it at all. So you're going to fix one value. So either you choose G1 is equal to 0 or G2 is equal to 1, or G2 is equal to 0 and G1 is equal to 1. You can either choose that. Okay, you can either choose any of these two conditions, because both these conditions will satisfy all these three equations. Because if they satisfy all these three equations, then only the remainder will become 0. And when the remainder becomes 0, then only g of x becomes a factor of x raised to 7 plus 1, which is one of the essential properties of the generator polynomial. So in that case, which value should you want me to choose? Let me choose one value. I will check. Let me just see for a second here. Maybe I will choose. Okay, let me choose. I'm going to choose this value. Okay, suppose we choose. Let me write both of them. Okay, I'll write both of them. Suppose if we choose. Okay, so like that I can explain to you the generated polynomial and the parity check polynomial now itself. So suppose if we choose. G1 is equal to 1 and G2 is equal to 0. Again, suppose if we choose G1 is equal to 1 and G2 is equal to 0. Okay, we can choose that because according to this, then here the remainder becomes 0. So if we choose this value, my g of x, that is my generated polynomial, is given by 1 plus the value of G1 is 1. So 1 plus x plus the value of G2 is 0. So 0 into x square is 0. So you don't have to write that. Plus x cube. This is my generated polynomial. That means if I choose G1 is equal to 1 and G2 is equal to 0, I can choose any one of them. So if I choose G1 is equal to 1 and G2 is equal to 0, then this is my generated polynomial. And if this is my generated polynomial, then I can simply write my h of x also very easily. And how to write h of x is, all you need to do is simply look at the quotient, because h of x is also a factor of x raised to n plus 1. H of x is also a factor of x raised to n plus 1. So which means in this entire process, other than this, the other polynomial which is a factor of x raised to n plus 1 is the quotient, right? We can't touch the remainder. The remainder is 0. So in this entire operation, the only polynomial other than this, which is also a factor of x raised to n plus 1, is the quotient. So therefore, this is your h of x. Your h of x is this value that you're seeing here. That is, what is the value? Let me write that value for you. Let me use another pen. The value is x raised to 4 plus g2x cube plus g1 plus g2x square, g1 plus g2x square plus what about 1 plus g2x, 1 plus g2x plus, and the other one is g1 plus g1 g2 plus g2, g1 plus g1 g2 plus g2. So this is, let me write it over here. Okay, so I hope you can see it over here. So this is your polynomial, your parity check polynomial h of x. Okay, but here, like I said, I have already chosen the value. Yeah, suppose we chose, right, g1 is equal to 1 and g2 is equal to 0. So what happens if I choose g1 is equal to 1 and g2 is equal to, in this entire equation, what will I get? I will get x raised to 4 plus, and this is g2 is 0, so this will disappear. And this is what? Here this is g2 is 0 and g1 is 1, so I will get x square, because this will become 1, right? So I will get x square plus, what about this? Here g2 is 0, so 1 plus 0 is 1, so I will get x plus, and what about this one over here? Here it's already written over here. See, g1 plus g2 plus g1 g2 is equal to 1. So g1 plus g1 1 2 plus g2 is also equal to 1. So this is equal to 1. So this is your h of x. This is how we create the generated polynomial and the parity check polynomial. You can choose any one of these two conditions. Okay, you can choose any one of these conditions, but once when you have chosen a condition, you should not change that condition. So which means I chose g1 is equal to 1 and g2 is equal to 0. So using those two values only, I found the value of g of x. This is my g of x. Okay, this is my g of x. What you're seeing here, g0 plus g1x plus g2x square plus g3x cube. Okay, this is my g of x, and I know that g0 and g3 should be equal to 1. So I don't know what is g1 and g2. So but I know that it's a factor of 1 plus x raised to n. So I divided and I found the remainder. I equated the remainder to 0, and then from there I discovered the two possibilities of g1 and g2. The two possible values of g1 and g2. That is either g1 is equal to 0 and g2 is equal to 1, or g2 is equal to 0 and g1 is equal to 1. Okay, so what I did is I chose the second condition. Okay, you can choose any condition, but once when you choose a condition, don't change it. So I chose this condition. So if this is my value, then what I'm going to do is I'm going to substitute those values in my g of x, and that is how I got this. Same way, h of x is also a factor of x raised to n plus 1, and the only factor in this entire process which is a factor of x raised to n plus 1 is the quotient, right? Other than the divisor, the quotient is also a factor of the dividend, right? So therefore I can take this factor and I substitute the value of g1 is equal to 1 and g2 is equal to 0, and that is how I got this. And this is the parity check polynomial. Right, the process of explaining it now is very simple. Okay, that's how you need to understand it. So now if you want, I can show you what happens. You can do this by yourself, right? You can do this by yourself. I want you all to do this by yourself. Suppose, okay, I'm telling you, in the rest of my class, in the rest of my video, I'm going to choose this condition. Okay, I am just simply going to choose this condition, that is g1 is equal to 1 and g2 is equal to 0. Okay, there is no rule on how to choose the values of g1 and g0. See, there is no rule. You can choose any condition you want, as long as the condition should be used as long as the remainder must be equal to 0. So since there are two conditions, there is no rule on choosing which condition you can use. You can choose whatever condition you want, but once when you chose a condition, never change the condition at all. So once I have fixed g1 is equal to 1 and g2 is equal to 0, then everywhere g1 should be equal to 1 and g2 is equal to 0, and that is how I got these two polynomials. Now if I chose, okay, suppose it's an if statement, if we choose g1 is equal to 0 and g2 is equal to 1, what would be your g of x in that case? I want you all to do that for your homework. Okay, what will be your g of x and what will be your h of x? Okay, I'm not going to write it over here, because if I write it, then you might get confused with like which condition I'm using. Don't forget, now in the rest of my video, I'm going to choose this condition. Okay, so you can do this as a homework. Suppose if we choose g1 is equal to 0 and g2 is equal to 1, what will be the value of g of x and what will be the value of h of x? Okay, because like I said, in both these cases, right? Like I said, in both these cases, in summary, what we have learned is that g of x into h of x is actually nothing but equal to x raised to n plus 1. G of x into h of x is actually equal to x raised to 7 plus 1. 7 is n. X raised to n plus 1. You see, there's nothing over here. This is 0 plus. There's nothing over there because there's no remainder. Remainder is 0 because both of them should be a factor of x raised to n plus 1. So that is how I got it. Okay. So now what I'm going to do is I'm going to explain to you how to create the generator matrix. Now I'm going to tell you how to create the generator matrix. Okay, so creating the generator matrix is also very easy, right? It's also very easy. So creating the generator matrix, if you want to create the generator matrix, we all know that the generator matrix, G matrix, right, has k by n dimension. K by n dimension, right? K by n means 4 by 7, which means 4 rows and 7 columns. Okay, so you know that, right? So now what I think is that we already know the polynomial. So looking at the polynomial, it is very easy to create the matrix. That is, here it is, g of x is equal to 1 plus x plus x cube, right? 1 plus x cube. Okay, so you know what, there's a shortcut method, there's a long cut method. There is a one method which does not need explanation, and you can simply look and simply draw the matrix by yourself. The other method is that you need to apply the theory or the explanation of how you got that. So what I'm going to do is, you see, this is g of x. So this will be your first row itself. Okay, how many rows are there? There are 4 rows, right? 4 by 7. This is a 4 rows. You are trying to create a matrix. Let me just draw that for you first. You are trying to create a matrix that looks like this right here. 4 rows and 7 columns. So what are those rows and what are those columns? That is what you're going to decide right now. So here g of x is this one. Okay, now you all learned in the introduction to cyclic codes that if you want to cycle shift this, what you need to do is you need to multiply this polynomial with x. Multiply this polynomial with x. So x into g of x. What is x into g of x? X into g of x is actually x plus x square plus x cube. All right, and then I'm going to cycle it. So how many times did I shifted it? I shifted it 1 time, right? So 1 time. Now what I'm going to shift it again. So if I'm going to shift it again, it will become x square into g of x. Okay, so what is x square into g of x? Multiply this with x square. You will get x square plus x cube plus x raised to 5. Oh, this is x raised to 4. I made a mistake. Okay, right? X into this is x plus x square plus x raised to 4. Likewise, x square g of x is x square plus x cube plus x raised to 5. Okay, and what I'm going to do is that I'm going to shift it, so it will become x cube g of x. Okay, so this will become x cube g of x. So if it means I'm going to multiply this g of x with x cube. So what will I get? I will get x cube plus x raised to 4 plus x raised to 6. Okay, so like I said, that there are 4 rows and 7 columns, and you just created those rows and columns over here. These are the 4 rows. This is the first row, this is the second row, this is the third row, and this is the 4th row. Okay, what is the first row? Let me see what is the first row looks like. The first row is actually, looking at this polynomial, right, it is actually 1 1. There is no x square, so 0 x cube 1. This is the first row, and actually precisely this is the first 4 elements of the first row. What about the remaining elements? There, how many columns should there be? There should be 7 columns, right? 4 by 7. This is 4 by 7, so there should be 7 columns. So 7 columns means 4 elements you have already written. So now put the remaining with zeros. This is your first row. Okay, now in the same way, look at the second row. The second row is where x square and x raised to 4, which means this is the second one, right? So the first one is 0, x is there, so this is 1. X square is, coefficient of x square is 1, so it's also here. Coefficient of x cube is 0, so this will be 0. And coefficient of x raised to 4 is 1, so it's 1. And the rest of them will be 0. Okay. Now let's look at the third row. The third row means I will be looking at this x squared gx. So the coefficient of x raised to 0 is 0. The coefficient of x is 0. The coefficient of x square is 1. The coefficient of x cube is 1. The coefficient of x raised to 4 is 0. The coefficient of x raised to 5 is 1. And then I put the other 0 over here. Okay. Now the last row here, if you look, this is the last row over here, right? So the coefficient of x raised to 0 is 0. The coefficient of x is 0. The coefficient of x square is 0. The coefficient of x cube is 1. The coefficient of x raised to 4 is 1. The coefficient of x raised to 5 is 0. And the coefficient of x raised to 6 is 1. And this is how you create your generate matrix. Okay. So now I think by now you have already understood what is the shortcut method. The shortcut method is that you don't have to write the these three rows. You see, once when you know how to write g of x, that is your first row. Okay, once when you write the first row, what you do is when you're going to write the second row, simply just shift it by 1 bit. That's all you need to do. Simply shift it by 1 bit. So in all the steps, so how many steps should there be? There should be 4 of them, because the value of k is equal to 4. It should be 4. Okay, and the remaining space you can fill it with zeros. Why? Because the number of columns is n. The number of columns is 7. That is why the remaining space you fill it with 0. That's all. This is how you create the generator matrix. Okay, and precisely this is actually, if you look at it, this is actually your generator matrix of non-systematic cyclic code. This is the generator matrix of non-systematic cyclic code. Okay, or precisely this is the generator matrix of NK non-systematic cyclic code. This is actually the generator matrix of non-systematic NK cyclic code. Why it is non-systematic? What is the meaning of non-systematic? Non-systematic means by looking at the code word, the input message as well as the parity check bits, the input bits and the parity check bits, both are all intermixed with each other. That is called as non-systematic cyclic code. Alright, and how do you know that this is a non-systematic? Because if it was a systematic, then there would have been an identity matrix inside. That is why. That is how I know that this is not a non-systematic cyclic code. Because if it had been a systematic, then there would have been an identity matrix. We know that, right? We have learned that from the NK linear blockers. That is, a systematic cyclic code means the part of them will be a message, the part of them will be your parity check bits. So if you want to get the message inside your code word, then the only way you can do that is only if the generator contains an identity matrix. Here there is no identity matrix. Identity matrix, when I say identity matrix, I meant this is the identity matrix: 1 0 0 0 0 1 0 0 0 0 0 1 0 and 0 0 0 1. Okay, it is the identity matrix should be of k by k, that is 4 by 4. Yeah, that is the property of the identity matrix. We call this as IK or I4. Okay, so there should be an identity matrix inside this. Unless and until there's an identity matrix over here, then only we can say that this is a generator matrix of a systematic cyclic code. So if you look over here, that identity matrix is missing. So what you can do is you can convert this matrix into a systematic cyclic code generator matrix. You can actually convert this by using what you all have learned from your 10th standard, and is called as row manipulations. All you need to do is make some row manipulations any way you like. Okay, just make some row manipulations in such a way that this part that you're seeing here, right, this part that you're seeing here should be looking like this. Okay, if you successfully created this part of the matrix that I'm circling right now, okay, maybe I'll circle with another pen just so that you'll understand. Okay, you see, if you make some modification, some row manipulation in this matrix so that you'll get this part of the matrix into an identity matrix, then you have successfully created the generator matrix of a cyclic code, systematic cyclic code. Right, systematic cyclic code. So what row manipulation do you want to have? Let me see for that. Let us see for that for ourselves. Okay, it's very easy. So let me see over here. When you look over here, okay, you see the last 4 should be 1 0 0 0. That is the first row of that is the identity matrix's first row is 1 0 0, which means the last row should be 1 0 0. You can see over here. Very good. See, the last row is already having 1 0 0, which means row 1 does not need any manipulation. Okay, you don't have to make any changes to row 1. Okay, no manipulation is required for row 1. Next, what about row 2? If you look at row 2, here you see, yeah, there also row 2 is also very good. See, row 2, they are in this part of the matrix, you need 0 1 0 0, and if you look over here, there is already 0 1 0 0 over here. Right, let me write that for you, 0 1 0 0. So no change is required for row 2 because row 1 and row 2 both have the rows of the identity matrix inside them. Therefore what I meant is that row 1 needs no change, row 2 needs no change, row 2 is row 2 should be itself. What about row 3? If you look at row 3 and if you especially look at the last 4 bits, if you want a systematic cyclic code, then this bit should be 0, but according to the matrix this bit is actually 1. So what you need to do is you need to apply some simple, very simple row manipulation, okay, some change so that this 1 will become 0. And how to make a 1 to 0? Remember this XOR function, right? So you need to understand the trick. How to make a 1 into a 0? You can make a 1 into a 0 only by adding another 1 to it, and no other place should it be 1. So see here, if you want this 1, if you want this 1 over here to become 0, then the only way to do that is to add some, you can use any row manipulation you like in such a way that it should make only this 1 to 0 and should not touch the remaining 3, because remaining 3 is actually correct. 0 1 0, 0 1 0. That is correct, but the first element should be changed. So what do you think I should do in that case? So row 3, what I need to do is, I'll take row 3 and I will XOR it, or I'll add it with row 1, because if I add the first row to the third row, then the last 3 elements over here 0 1 0, that will be unchanged, and this element will become 0 because 1 plus 1 is 0. So this is a manipulation I make for row 3. That is row 3, I will change it to row 3 plus row 1. Okay. Now what about row 4? Speaking of row 4, what we talk about row 4 is that we need 1 only over here and the rest of them should be 0. But if you look over here in this last 4 bits, the first bit and the second bit, that is this bit and this bit, is actually 1. So what I need to do is I need to make it 0. So what do you think I should do for that? You can use any tactic you like, but make sure that this values doesn't change. You should get 0 0 0 1, nothing else. So to get that, you see, if I take this row and if I add it with this 1 will become 0. If I take this row and if I add it with this, then this 1 will become 0, and none of the other elements will be touched because those elements are all zeros. So which means row 4 is nothing but row 4 plus row 1 plus row 2. Okay, so if you make these row manipulations, then this will become a generator matrix of a systematic cyclic code. So let me just write that for you. So let me see. So first row, no change, right? So 1 1 0 1 0 0 0. Second row also no change. 0 1 1 0 1 0 0. Third row is nothing but third row plus first row. So let me add them together. It's 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0. And what about the fourth row? Fourth row is nothing but the first row, second row added with the fourth row, which means 1 plus 0 plus 0 is 1, 1 plus 1 plus 0 is 0, 0 plus 1 plus 0 is 1, 1 plus 0 plus 1 is 0, 0 plus 1 plus 1 is 0, 0 plus 0 plus 0 is 0, 0 plus 0 plus 1 is 1. There. So now, from the generator matrix of non-systematic cyclic code, I have created the generator matrix of systematic cyclic code. So this is the procedure of creating the generator matrix of a systematic cyclic code. And how do you create it is, first you find the generator matrix of non-systematic cyclic code, and then you create the row manipulation. By using some simple row manipulation, you can create the row in such a way that the second half over here you'll get an identity matrix. Okay, it should be a part identity matrix. So to get that part identity matrix, you can use some simple row manipulation, and that is how you see. If you look over here, see, you have created an identity matrix. So from looking at the identity matrix, I know that this matrix, what I'm seeing here, is actually the generator matrix of a systematic cyclic code. Okay. So this is how we create the generator matrix of non-systematic as well as systematic cyclic code. Now, likewise, let us see how to create the parity check matrix, H matrix. Okay, so speaking of H matrix is also very simple. It's very easy. H matrix also, what you need to know what is the dimension of H matrix. So the dimension of H matrix is, how do you say it? You say it like this, right? N minus k by n. That is, it has 3 rows and 7 columns, right? 7 minus 4 is 3. So 3 rows and 7 columns, n minus k rows and n columns. So we know that, right? So that's one thing we have learned. So let me write the H matrix. So the value of my parity check polynomial that I have already found out was this, right? This is my parity check polynomial. Let me write this, x raised to 4. Let me just write it over here. Let me write in the normal way. That is 1 plus, okay, 1 plus x plus x square plus x raised to 4. Okay, let me write it the normal way, and then I will tell you how to write it. Okay, so now next thing what I'm going to do is that I'm going to take its reciprocal. I'm going to take the reciprocal of h of x. Okay, that is what I'm going to do. Reciprocal of h of x. And reciprocal of h of x is nothing but, we call it like this, h of x inverse. This is how we use the name. Okay, and so h of x inverse. So what is h of x inverse? H of x inverse is equal to nothing. Just all the powers will become negative. That's all. So here this is here x raised to 0, but x raised to minus 0, so x raised to plus 0 minus 0 both are same, right? So this is 1 itself. 1 plus x raised to 1 will become x raised to minus 1, plus x raised to 2 will become x raised to minus 2, plus x raised to 4 will become x raised to minus 4. Okay, now, okay, so now you did this. Now what I'm going to do is that, you see, we all know what the H matrix looks like. The H matrix should have n minus k rows and n columns. Yeah, you're seeing that over here. Okay, that is, it should have 3 rows and 7 columns. So what are those 3 rows and what are those 7 columns? Well, the 3 rows are, if you look very carefully over here, the generator matrix, what you did is you multiplied, you took the generator matrix one value, that value itself, and then what you did is you multiplied it, one with x, the other with x square, and the other with x cube. So how many times has it been? 1, 2, 3, 4, and the remaining times is now what? 3 times. What I'm going to do is this, x raised to 5 h of x inverse, then I will find the value of x raised to 6 into h of x inverse, then I will find the value of x raised to 7 No, I forgot x raised to here. It is stopped with x cube, right? So which means x raised to 4 into h of x inverse there. These are my 3 rows. These what you're seeing here are my 3 rows, right? That is, let me just say x raised to 4 into this. So it means multiply this with x raised to 4. I will get x raised to 4 plus x cube plus x square plus 1. If I multiply with x raised to 5 with this, I will get x raised to 5 plus x raised to 4 plus x raised to 3 plus x raised to 1. X raised to 1 is x itself. And next I will multiply this with x raised to 6. I will get x raised to 6 plus x raised to 5 plus x raised to 4 plus x raised to 2. Right? So this is what I get if I am multiplying with each of these values with h of x inverse. This is the polynomials I will get. Okay. Then what I'm going to do is that it's very simple. All I need to do is, these are my rows, so I will put that over here. So this is actually 1 plus x square plus x cube plus x raised to 4. So that means here the coefficient of x raised to 0 is 1. The coefficient of x is 0, right? The coefficient of x square is 1. The coefficient of x cube is 1. The coefficient of x raised to 4 is also 1. Okay? 1, 2, 3, 4, 5, which means there should be 7 columns, right? Which means you need to put 2 more zeros over here. This is the first row. Then look at the second row, x raised to 5 into h of x inverse. This is your second row. So second row means it starts with the coefficient of x raised to 0 is 0. The coefficient of x raised to 1 is 1. The coefficient of, there's no x square over here, so therefore the coefficient of x square is 0. The coefficient of x raised to 3 is 1. The coefficient of x raised to 4 is 1. The coefficient of x raised to 5 is also 1. Then you put a 0 over here. The last column, there's this one right over here. So the coefficient here, the coefficient of x raised to 0 is 0. The coefficient of, there's no x over here, so therefore the coefficient of x is also 0. The coefficient of x square is 1. The coefficient of x cube is 0. The coefficient of x raised to 4 is over here, so it's 1. The coefficient of x raised to 5 is over here, so it's 1. The coefficient of x raised to 6 is also 1. This is your parity check parity check matrix of, this is also actually the parity check matrix of non-systematic cyclic code. Okay, this is the parity check matrix of non-systematic cyclic code. Okay, non-systematic. How do I know it's non-systematic? Again, because if it had been a systematic, then there would be an identity matrix somewhere in this, either over here or over here, but there is no identity matrix anywhere over here. So this is a non-systematic cyclic code. That's how I know. Now next is, what is the shortcut method of writing the matrix? I use the long cut method. If you all remember, if you all know, if you understand how to write the shortcut method, the shortcut method is actually, how you do is, you see, you look over the polynomial over here. Okay, what is this? This is actually how to say it? 1 1 0 1 1, right? Sorry. This is 1 1. Sorry, I made a mistake. This is 1 1 1 0 1. Right, this code, right, I'm writing this code like this: 1 1 1 0 1, right? 1 1 1 0 1, right? Let me see, 0 1 2 3 4. Okay, see, there is x, so there is x raised to 0 over here. This one represents x raised to 1. This one represents the coefficient of x raised to 2. This 0 represents the coefficient of x cube, because there is no x cube over here, and this one is actually the coefficient of x raised to 4. Okay, so if you want to write the H matrix in a shortcut method, what you need to do is, first you take its reverse. You reverse the numbers. So instead of 1 1 1 1 0 1, it becomes 1 0 1 1 1. Okay, you reverse the numbers, and then you can, so how many numbers are there? 5 numbers, right? So since you need 7 columns, the remaining space you put it 0 0 0, and then that's all you need to do. Okay, just reverse numbers. After reversing numbers, if you want to write the second row, shift it by 1 bit. If you want to write the third row, shift it by 1 bit, again shift it by 1 bit. If you want to write the fourth row, again shift it by 1 bit, and so on. This is simply shifting, which means once when you fixed one row, how do you get this row? By simply reversing this, okay? Reverse this, you'll get the first row, and after that, to write the remaining rows, simply shift towards right by 1 bit, just like your generator matrix. But in your generator matrix, you don't have to take its reverse. That is one thing you need to use a shortcut method. For those of you who are going to apply shortcut method, you can apply the value of your first row the same way as your polynomial itself. The same way as your polynomial itself, and then in the remaining rows you just need to shift it by 1 bit to the right. But in the H polynomial, in the case of an H matrix, if you want to create the matrix from the polynomial, before applying the first row, you need to reverse it. Reverse the polynomial, reverse the coefficients, reverse the bit sequence, and then that is your first row. And that is your first row, shifted by 1 bit, and you'll get the second row, shifted by another bit, and you'll get the third row, and so on. Okay? And just make sure that these dimensions are all being satisfied. That's all. If you want to create the parity check matrix of a systematic NK cyclic code, what you need to do is simply make sure that the first part of the identity matrix, or the first part of the H matrix, is an identity matrix, okay? Because if you look over here, okay, if you see over here, this is the identity matrix, right? The second part is the identity matrix, and the first part is the parity matrix, okay? That means here I defined my G in this term. I defined my G matrix in this form, that is G is equal to PIK, right? That is G is equal to, let me write it, PIK. G is equal to PIK. So which means if G is equal to PIK, then H, to find the value of H, the value of H should be, the first part should have the identity matrix followed by P transpose. That is how we define the generator matrix and the parity check matrix of a systematic cyclic code. Systematic cyclic code, because we all know that an NK cyclic code is actually an NK linear block code with cyclic properties. That's all, right? So all the properties of NK linear block code are also the properties of NK cyclic code. So in that case, see, so if the first part if the first half is parity and the second half is identity for generator matrix, then the first part will be identity and the second part will be the parity bits of the parity check matrix. Also, reverse is also true. That is, if the first half of the generator matrix is identity and the second part is parity check matrix, then the second part of the parity check matrix will be identity matrix and the first part will be the parity matrix. So that is how we actually define it. So here, what you need to do is, if I want to derive the systematic parity check matrix from here, from the non-systematic parity check matrix. So to do that, all I need to do is again apply what you call as the row manipulation, symbol row manipulation, and what you are trying to find is you need to have an identity matrix that is looking like this, that is I3. 7 minus 4 is equal to 3, right? So you should have I3. I3 means what? 1 0 0 0 1 0 0 0 1, which means you need to have 1 0 0 0 1 0 0 0 1 over here. That means over here, this first 3 over here that you're seeing here, you should have the identity matrix, okay? And to have that identity matrix, what I should do is I need to apply a symbol row manipulation. So let's look at the first row, row 1. Okay, what manipulation should I make row 1? I want row 1 to have this one 1 0 0 over here, but instead of 1 0 0 I have 1 0 1, which means I need to make this 1 into 0. So the only way to make this 1 into 0 is by adding another 1 to it, right? Adding another 1. So which row should I choose? I'll choose row 3, right? So which means row 1 is nothing but should be modified into row 1 plus row 3, right? Row 1 should be nothing but row 1 plus row 3. That is one thing. What about row 2? If you look at row 2, here the first part or the first 3 is 0 1 0, which is exactly the same as your second row of your required identity matrix. So which means no change is required. So row 2 you can leave as it is. What about row 3? Row 3 also, if you look over here, it is 0 0 1, and that's exactly what you need, 0 0 1. So therefore row 3 also does not need any change. So this is the only change you need. That is, only row 1 needs to be changed, right? So in that case, then the H matrix is actually equal to, of a systematic cyclic code, the H matrix is actually equal to, let me see, row 1 is first row and the third row. So 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0, 1 plus 0 is 1, 1 plus 1 is 0, 0 plus 1 is 1, 0 plus 1 is 1. Second row, no change, 0, 1, 0, 1, 1, 1, 0. Third row also no change, 0, 0, 1, 0, 1, 1, 1. So see, from here I have created the, this is what you call as the parity check matrix of systematic cyclic code. Okay. In case systematic cyclic code. Now all you need to do is simply compare your the systematic parity check matrix with the systematic generator matrix. Okay, systematic. All you need to do is simply compare, and you can see for yourself that it satisfies all these equations that you studied. That is, it satisfies this equation, it satisfies this equation, because here if you look carefully, here what is the value of P? The value of P is actually, look over here, this is P, right? 110, 011, 111, 101. This is your P matrix, your parity generator matrix. Now if you see over here, this is actually nothing but your P transpose. See? So you can simply just compare and enjoy for yourself how everything just now beautifully connects each other. Okay, so this is how we explain about the parity check matrix and the generator matrix of both systematic and non-systematic cyclic code. So in summary, what we did over here is that we discussed about the generator, how to create the generator polynomial and the parity check polynomial of an NK cyclic code, right? We start with this. We start with the essential properties of the generator matrix, and then from here we satisfy all these properties. We create the generator matrix, we create the generator polynomial, and after creating the generator polynomial, we choose the value of generator polynomials, we choose the value of the constant so that the remainder becomes 0, and you can choose any one of them. I choose g1 is equal to 1 and g2 is equal to 0, so therefore this is my g of x and this is my h of x, and likewise I have created my h matrix, and I have also created my I have created my G matrix of non-systematic cyclic code, and from the generator matrix of non-systematic cyclic code, I created the generator matrix of my systematic cyclic code. Likewise, in the same case, in the case of a parity check matrix, from here I created the from this polynomial I created the parity check matrix of my NK cyclic code, and then after that from here I create from the parity check matrix of non-systematic cyclic code, I created the parity check matrix of my systematic cyclic code. Okay, so this is what this is the procedure of creating it. Okay, that is, first, if you want to create a systematic cyclic code, if you want to create the matrix of a systematic cyclic code, you first create the matrix. You first create, whether it is generator matrix or parity check matrix, you first create the matrix of a non-systematic cyclic code. Then using simple basic row manipulation, you can convert that matrix of non-systematic cyclic code into a matrix of systematic cyclic code. Okay, so this is what we